Unit 2, Lesson 2, Domain and Range. So these are two new terms that you guys are unfamiliar with. So let's look at the definitions first. So the domain of a function represents all the possible x values that generate a point on the function. So for example, if I had a function like this, it's just a linear relation. It started here at x equals -2, and it stopped at x equals +3. Okay, there's my function. The domain would include all the x values in between the boundaries of this function. Something like x equals +10 would not be part of the domain because that x value does not generate a point on this line. The line starts here and stops here. Any x value outside of those boundaries would not be part of the domain. When you hear domain, think x values. Okay, the range, think y values. So the range refers to the set of y values that are present in the function. For example, if I have a function like this that starts here at -1, and let's say it ends here, which happens to be at +5. Okay, if you're reporting on what the range is, you want to report on all the y values that are part of this function. So it would only be the y values between -1 and +5, right? -2 is outside those boundaries. -2 is not part of the range of this function because -2 is not part of a point on this function. Okay, we know in math there are a bunch of different types of numbers, right? There's fractions, decimals, negative numbers, positive numbers, 0. Okay, and we actually can group some of these into the following categories. So the first category is called real numbers, okay, and it's denoted by a symbol like this. So to draw it, you just do an R like this and then add an extra line there. And real numbers, it's the biggest category. Basically all types of numbers. It includes fractions, decimals, whole numbers, 0, okay? So real numbers include them all. Natural numbers are a little bit more selective, okay, and you can write this, just do a regular N, and then add an extra line like that. That's the symbol for natural numbers. Okay, so natural numbers only include positive integers. So an integer is something that's not a fraction, so just whole numbers. Okay, and the natural numbers do not include 0 and are only positive integers. So basically, they're just positive whole numbers greater than 0. So a natural number would be like 1, 2, 3, 4, etc., etc. Integers is our next group, and it's represented using a Z with an extra line. And integers are a group of numbers that represent any number as long as it's not a fraction. So any negative numbers, 0, positive numbers, just no fractions. So things like -10, -9, -8, zeros in there, 1, 2, 3, okay? So negative, positive whole numbers, and 0 are integers. And finally, the last group or category is rational numbers. And we represent rational numbers using this symbol. It's a Q, and you can just kind of put a line through it. That means rational number. Okay, and what is a rational number? A rational number is a fraction or decimal. Okay, and these 4 categories, or these 4 new symbols, are going to be used when we write down the domain and range of a function. So, if you are given a function and you are asked to write the domain and the range of it, here is what you would do. Okay, so you always write D for domain, R for range, and then equals, open a bracket, and then inside of the brackets you talk about what x values are present in the function. Okay, so if the function you're given encompasses every single x value possible, for example, a true quadratic, written like this, you know that that quadratic extends, so every single x value is going to be a part of this function, right? All negative numbers, all positive numbers, all decimals, all fractions, 0, okay? Every single x value is present in that function, or every single x value generates a point on that function eventually, right? If we just extend this quadratic, then you would say the domain of this function is an element of all the real numbers. So x is an element of all the real numbers. Now, there's always a second part of the domain. So if there was a restriction, like maybe you had, a break in the graph. So for example, you had a graph that looked like this. Let's say that this break in the middle was at x equals 2. You would write your domain, but then you'd include a restriction. x cannot equal 2, because on this graph there is no value associated with x equals 2. Same thing when you're asked to write the range. So start by writing your r equals, open your bracket, so if the range encompasses all y values, you'd say y is an element of all the real numbers, because the real numbers was a group that encompassed everything. And then if there's any restrictions, you write them here. We're going to go through a lot of examples now, and I'm going to show you how to write domain and how to include restrictions if there are any. So don't worry just yet if this is a little bit confusing. Okay, so determine the domain and range of the following graphs. Let's start with part A. Okay, and remember, arrows on the end of the line means that that line extends to infinity. Let's start with the domain. D equals, open your brackets. So which x values generate y values on this graph? Okay, and because this line is just extending throughout everything, any possible x value would generate a y value. So you say x is an element of the real numbers, close your bracket because there's no restrictions, right? Just absolutely any x value that you can think of will generate a y value on this graph. Now let's look at the range. So which y values are part of this function? Well, it's the same thing, right? Because this is a linear relation that's extending on both sides, no matter what y value you pick, it's going to be part of a point on that line. Okay, so y is also an element of the real numbers. Okay, and just to review, remember this is a linear relation. Okay, the next one we have is a quadratic relation. Okay, and arrows mean that it's extending. Let's report on the domain and the range for this quadratic relation. So first, the domain. Which x values generate a y value on this quadratic? You're going to realize every single x value has an output on this quadratic, right? Because this extends to infinity, right? So every single x value, negative, positive, decimals, fractions, 0, will all have a point on this graph. So we say x is an element of the real numbers. Okay, the range is a little bit different. Is every single y value a part of a point on this function? Okay, well, you might say that, yep, every single y value on the graph above this line generates a point, right? Because this y value has a point on the graph. This one does, okay? But any y value below that line does not generate a point on the graph. So let's see where that line is. That line is at y equals 3. So we could say the range for this function is an element of the real numbers as long as y is greater than 3, right? So any real number greater than y equals 3 will generate a point on this graph. So our range for this function is y is an element of the real numbers, but then there's a restriction as long as y is greater or equal to 3. So part C is the square root graph. Okay, let's look at the domain of this graph. So which values of x generate a point on this function? Okay, and this time it's not everything, right? There's no negative values of x that would generate a point on this function. It's only positive values to the right of this line. Okay, so only x values over here are going to generate points on the graph. So let's find out where this line is. Okay, it looks like it's at x equals 2. So then our domain is going to be x is an element of the real numbers as long as x is greater or equal to 2. Okay, and that makes sense. Any decimal, fraction, whole number greater than x equals 2, so all these guys in here will generate a point on the graph. So that is the domain of this function. Now the range of this function is going to be any y value greater than 0, right? Because this graph does not extend below the x-axis. So this graph will only have points with positive y values. So y has to be greater than 0. So the range here is y is an element of all the real numbers. As long as y is greater or equal to 0, it will generate a point on the graph, right? Because here's 0, it has a point on the graph. Here's y equals 4, it generates a point on the graph. Here's y equals 8, it generates a point on the graph, you know? And as this extends and extends and extends, you'll see that any value that's greater than 0 on the y-axis will generate a point on the graph, so it's part of the range. Okay, let's look at part D. Okay, this is a cubic function, and I think it's pretty easy to look at this and say that because this cubic function is extending to infinity, all possible x values will generate a point on this function, and likewise all values on the y-axis will also be part of points on this function. So the domain of a cubic function is x is an element of all the real numbers with no restrictions, and the range is y is an element of the real numbers, again with no restriction. Okay, part E is going to be a new graph for a lot of you. This is called the absolute function. So it just means that you always, to figure out the y value, you take the x value and you take the absolute value of the x value. So if the x value was -2, you would just take the absolute value of that, so just 2. Okay, so let's report on the domain and range here. And sorry, there should be arrows here. Which x values would generate points on this graph, right? If this is extending until infinity, it's going to cover every single x value. So the domain here is x is an element of all the real numbers, and there are no restrictions. Let's look at the range though, okay? Because this graph, so any y value below this line here will have a point on this function, right? Because a y value of 3 would have a point right there, okay? But a y value of 5 does not have a point on the graph. So the range for this function is an element of the reals as long as y is less than 4. Okay, I'm saying less than or equal to because it could be 4, right? 4 will have a point. Okay, this is called a reciprocal function. Let's figure out the domain and range. So when looking at the domain, what possible x values will generate a point on this function? Okay, and any number to the left of kind of right here on the x value will generate a point on the function. Any value to the right of kind of about right there will also generate a point. But there's this spot right in the middle, okay, whatever that x value is, that cannot generate a point. And we call that a vertical asymptote. So it's essentially this gray area where there are no points. Okay, so I've drawn in my vertical asymptote there, and if you look, the graph gets very close to that vertical asymptote, but it never touches it. Okay, same with this side of the graph. The graph gets very, very close to that vertical asymptote, but never touches it. Okay, so that'll be a restriction in our domain. So the domain for this function is x is an element of the real numbers as long as x is not 4. Okay, because that represents that vertical asymptote. That's a restriction. Okay, now when we report on the range, so it's a similar thing happening here. We have a horizontal asymptote at 0, right? So every y value above 0 is a point on the graph, and every y value below 0 is a point on the graph. But we have a horizontal asymptote right at 0, meaning the graph gets very close to 0 but never touches it. And likewise here, the graph gets very close to 0 but never touches it. Okay, so our range is any y value as long as y is not 0. So we would say y is an element of the real numbers as long as y is not 0. So there is a restriction there for reciprocal function. So we now know how to determine the domain and range from a graph. We need to learn how to determine the domain and range from an equation only. So we need to look at the equation and ask ourselves, what type of an equation is that? Okay, example A is a reciprocal function. So if you look back up in the note, that's this type of function right here. So we know when reporting on the domain and range, it's going to have a vertical and horizontal asymptote, and that's our only restriction in our domain and range. So let's start with the domain. Okay, the domain is going to have a restriction on an x value, okay, and that's going to be where the vertical asymptote is. So we need to figure out what our restriction is, and we can find that out by setting our denominator to 0, right? It's like when we figured out our restrictions in the last unit. Okay, so first step is find your restrictions, and then we can incorporate that into our domain. So what can x not be? So our first restriction is that x cannot be 4. So we know our domain is x is an element of all real numbers as long as x is not 4. So that must mean that that vertical asymptote is at 4. For our range, we're going to have a horizontal asymptote. And if you remember on the base graph on the last page, it was at 0. Okay, so as long as our graph hasn't shifted up or down, we know that our horizontal asymptote is still at 0. So this function had a vertical translation up or down, it would have some sort of a k value here. So because this does not have a k value, there is no up or down translation, so this function will still have a horizontal asymptote at y equals 0. So that's our restriction for the range. So for the range, y is an element of all the real numbers as long as y is not 0. Okay, let's check out part B. So find domain and range for this function. Let's go ahead and find our restriction on the domain. So our restriction on the domain is going to be set 2x plus 11 equal to 0 and solve. So x cannot be negative 11 over 2. And because this is a reciprocal function, that must be where the vertical asymptote is. So the domain is equal to x is an element of the real numbers as long as x is not negative 11 over 2. Okay, likewise, there is no k value here, so we know that this reciprocal function has not shifted up or down from the base graph. So the range is y is an element of the real numbers and y cannot equal 0. Okay, let's figure out the domain and range of parts C and D. So these are both quadratic functions. To figure out the domain and range of a quadratic, it's important that you know the direction of its opening and where its vertex is. This function opens up because the a value is positive, and its vertex is located at 4 and 6. Okay, so you can kind of draw yourself a quick sketch just so you can visualize. So there's the vertex and it opens up. Okay, so the domain of a quadratic function is going to be every real number. So your domain is going to be x is an element of the real numbers and there's no restrictions on this domain. The range, however, is going to be y is an element of the real numbers, but there's going to be a restriction, right? Because all y values below y equals 6 do not generate points on the graph. So as long as your y values are greater or equal to 6, they generate points on the graph. So the restriction is y can be any real number as long as y is greater or equal to 6. Okay, so we have learned how to come up with the domain and range from a graph, an equation. Now the last thing is determining the domain and range from an application problem. So the only thing that's different is sometimes in an application problem there's going to be certain restrictions that are present because of the scenario in the problem. Okay, let's look at example 3. So we have a graph of this function where h is the height in meters since a football was kicked and x represents time. Okay, so as time goes on, this is the path of the football. Okay, let's determine the domain and range. So usually in a quadratic, the domain would be any number, right? X is an element of the real numbers. But because this is an application problem, we know that time cannot be negative, right? You don't have negative time. The domain for this problem can't incorporate any x value less than 0. Likewise, we know that the football hits the ground right here, which looks like it's at 4.75. So for this word problem, the domain can't include any x values greater than 4.75, because that's when the situation is done. The football has landed. Our domain here is x is an element of the real numbers, but there's a restriction. X has to be a value between 0 and 4.75. So it has to be greater or equal to 0, but less than or equal to 4.75. Same with the range. The football can only go above ground. Okay, when you kick a football, it doesn't go in and below the ground. So your range cannot encompass any negative y values. Likewise, he's only so good at kicking that football, right? He can only kick to a height of 28 meters. So our range cannot include anything higher than 28 on the y-axis. So therefore, our range is y is an element of the real numbers, but y has to be greater than 0 because that football does not go below the ground, but then it has to be less than its max, which is 28. So as you can see, because of this application problem, we have certain restrictions in place, right? If this wasn't an application problem, if it was just what are the restrictions on this graph and there were arrows here, your domain would be any real number and your range would be any y value as long as it's less than 28.